So for today's class, we are going to continue, but this time we're going to go over the generative adversarial networks, GANs. Probably you have heard of GANs as like a pretty popular. What was that? Yeah. Again, to just quick refresher, we know that what's the story. We're going to for this probability of this data, find some model family that has the minimum distance between these two. That's the overall goal. And so far, we have seen autoregressive models, which every data that or every pixel that being generated is kind of depends only on the past. Then we saw the variational autoencoders, which basically probability of a data point comes from some sort of like collection over all latent variables, basically. So the marginal over x, so likelihood of x comes basically from this joint distribution of x and z across all possible z's, right? And one thing we learned about the variational autoencoder was that you can break down this definition using some sort of like importance sampling, because we're like, oh, we don't know probability of z. So what we do instead, basically, we introduce some suggestive, basically, distribution to use basically to sample the data to z basically from there. And this was the important sampling part. And then based on this one, you could basically write this as expected value for z's that come from the Q, because the way that this looks like over, so sorry, apply log. Yeah, apply log to make it, just separate that piece. Minus log of. Okay. So we saw this term, and because we applied log, technically this is log of p of x, technically. One thing we also learned was that you have this Jensen inequality that expectation, basically log of expectation is always greater than expectation of the log. So that's technically when you applied log and we move the log inside, this becomes the expectation of the log. So this term is the lower bound for the basically the original log. So for z that come from this Q, and this basically called elbow, right? This was the elbow term. Then we also say that, okay, we know this is the elbow, we know this is the lower bound, but now we can have a different version of the VAE here, and those versions come based on how you define this P of x and z, that's joint distribution. So if you, instead of basically P of x and z, so we know that P of x and z could be written in two ways. Either one of this, depending on the scenarios, you basically can decide which one you want to use. So the only difference will be that instead of this term, you're going to use this, or you're going to use that. Then the difference basically became, you have these terms. One of them becomes log of this in one scenario minus log of d given x qz. So that becomes one version. The other version basically becomes d that comes from qz. This becomes p d minus expected value q. log probability of this. Sorry, this is reverse. X, Z, we always read this here, probability Z. Okay. So these are two scenarios, two versions of this VAE basically that you can get. Then the last thing about VAE we saw that was because in neural network that the VAE that you create, there is a point that you have this sampling, and that sampling has issues when you try to do backpropagation through the sampling node. So in order to get rid of that sampling, in VAE, we introduced this basically called reparameterization trick. And that trick basically says that instead of having Z that we sample, we're going to define Z as mu plus covariance times epsilon, where epsilon is basically noise, sample noise. So instead of we sample Z, we have a deterministic equation for Z. This is the noise sample we sample. So by doing so, this reparameterization trick, when you do backpropagation, you don't need to backpropagate through a stochastic node. You always have this deterministic node that you can basically backpropagate through, right? So this becomes basically everything that we saw for variational autoencoder. The problem with variational autoencoder was that, well, you still have this untractable basically distribution because of the way that in order to define X, you need to actually go over all possible Z's, right? And that's where we introduced normalizing flow models. Normalizing flow models, the idea was that could we define some transformation, some sort of bijective functions between X and Z that what it does basically, we say that let's assume X is a function over Z, and we want this function to be invertible. That means you should be able to just take the invert of this, and get back to Z. We also saw that you can write this again at this form, and you can write this as this form. Okay, so the idea was that we want this function that can do basically perform this transformation, but if you just simply transform from one variable to another variable, the problem that we have is the distribution won't basically change. You need to have a way also that the distribution of X, you could basically write it with respect to Z and Z with respect to X. And what we did in normalizing flow, we used basically a change of variable formula that says probability of X comes from probability of Z times determinant of basically Z with respect to X inverse. Okay. So technically, this is determinant of Z with respect to X. Inverse comes in it as we will see. And depending on which direction are we going forward or inverse. So this X generated from Z, this is a forward direction. This Z generated from X, this is an inverse direction, right? So now here, if you think about P of X, you can write it as P of Z. Z is technically, where is it? F inverse X. So we can have P of F inverse X instead of Z. Then we could also say that, well, okay, so inside this here, we have determinant of F inverse X with respect to X. Okay, so basically we replace that here. Now the other thing is that we can still basically rewrite this. So we can also introduce this, take the inverse outside. So in that scenario, we have that this becomes, we can write it as P of F inverse X determinant of F Z the inverse. Because when you take the inverse outside, basically that change of variable basic also happens, right?
F X X.
So this becomes Z, because if you think about this, this is actually equivalent to that. So let's do one thing. So we have Z equal F inverse F D, right? So if you have a function hx and hx equal, or let's say hz equal u v z, or let's just say h. I have h in h equal u v z. If you take a derivation of h with respect to z, we can basically take using the chain rule, this becomes derivation of u with respect to u of x, let's say, with respect to x, because whatever is in it, let's assume it's x, times derivation of v of z with respect to z, correct? So here, if we take a derivation of z with respect to itself, which is 1, but let's take a derivation of this. So this becomes derivation of f inverse x with respect to x times derivation of fz with respect to z, and that's equal to 1, because this is 1, right? So given that can say derivation of f inverse x over x equal derivation of f z over z inverse, if you take it to the other side, right? So this and this, they are technically the same thing. Make sense? Okay, so that's the idea of normalizing flow. Is just you need to do some, like have a function that basically is can transfer one to the other one and is like invertible, and we use this change of variable formula to define the probabilities. And what we also learned in normalizing flow was that when you transform from one variable to the other variable, the distribution basically changes. It's like either becomes wider or basically becomes like a taller, shorter, depending on the width, which is the compressing or basically a stretching, depends on the derivation of the gradient of the function with respect to the variable. And the probability, the height, comes from this change of variable formula. And that's basically how you define the new distribution. And the idea is that to go from a simple distribution Z to more complex distribution. Is that clear? So that was the idea of normalizing flow. And the thing about all of these models so far that we have seen is that, well, they all kind of train some sort of like KL divergence or maximum likelihood estimation, like these models that we have seen so far, right? Now, the idea about maximum likelihood estimation is that, well, it's good. There's a reason that we are using maximum likelihood estimation often. That one of them is actually called optimal statistical efficiency. Optimal statistical efficiency says that if you believe that there could exist, like there's under certain scenario, which most of the time is not actually that valid, you could say that with a complex model, a model that is like a basic expressive enough, like a really good model, if we believe that there is a chance that this model could produce a theta, that means has set of parameters, somehow that the probability of theta and data becomes equal. That means a perfect model. So basically, again, what does it say? It says under some assumption, if you believe that for a certain model, that model has a chance to produce perfect data, optimality, then with enough data points, like if the number of data points increases to infinite, maximum likelihood estimation is actually the fastest way to find that likelihood, to basically to solve this problem. So that's one of the reasons we actually use MLE a lot, because it has this basically optimal statistical theory behind it. Okay, which again is not always the case, but still we are utilizing it. Now, we also know that if you use likelihood, that's a maximum likelihood, maximizing the likelihood means doing a better basically compression on the data. And compressing the data, lossless compression, means you learn about the data. So that's the idea that we had so far. Now, always this class is this. Direction is really difficult. So these are the type of model that, for example, so far we have seen that they are using maximum likelihood estimation. And then all of this basically have this idea of like we have some parameters that we want to learn it. We get enough data and we use MLE, we learn that basically probability. Now, the idea about GANs is actually GANs are type of like a maximum, like a likelihood free models. The idea here is that could we basically from some random noise generate image without a need for learning that basic explicitly defining that distribution? Because all of the models before, they explicitly work on the distribution. The idea of GANs is that, well, I don't want to have an explicit definition, and I want to just be able to generate data without a need to have likelihood concept and likelihood learning. So that's the overall goal that we had in GAN, to generate data, but in a likelihood-free, basically, way. Now, the question comes here is that, well, let's say you have this, we want to understand why we want to get rid of likelihood. If likelihood learning, maximum likelihood, for example, it works really good, why we want to do likelihood-free techniques. And there are a couple of cases that we want to review. The first one is like the optimal generative model, okay? And optimal generative model becomes scenario that when you have this model, when it produces data, the probability of data is just like a really high quality, basically, right? The sample quality is really basically good, and it gives the really good high likelihood to the test data that you have. So that's an optimal generative model. Then you could also have imperfect model. Imperfect model is a model that basically could give you a really high likelihood, but the quality of the images are really bad, right? That becomes an imperfect model. And this basically, the relationship, this existing was proven as part of this paper by Tessis et al. Like 2016 is a really interesting paper on this concept of likelihood and why focusing on likelihood actually could cause having a bad model, models that have a high likelihood, but actually the quality of the images are pretty bad. Now, in order to understand that better, let's look at one example. So let's assume we have this model. You have this model that it looks like this. So probability of data comes from it's like some sort of like a Bernoulli over probability of the data, actual data, plus 99% noise. So this model, basically 99% of the time, it produces noise technically, right? So you have P of X that comes again from 0.01 P of data over X plus P of, let's say, generator over X, or this quality and noise. Now we want to understand that why likelihood basically learning will fail in a model like that. Right? Again, this is a scenario. You developed a model, but this this model that you have, 99% of the time, it actually just produces noise. 1% of the time, it produces data. But if we want to see that if we use likelihood learning, why we will fail, okay? So if you have, for example, something like this, log A plus B, okay? And where, let's say, for example, B is greater than 0 and A is greater than or equal to 0, sorry, reverse. This log AB and A plus B, because it's monotonic, is always greater than equal to log A, okay? Now, if we apply, let's put a log here, right? This becomes log of this term plus log of this term. So we know log P of X is always greater than or equal log P of theta X. Okay. And we can break this log. This becomes log of basically P of theta X. And log of 1 over 100, you can also make it log of 1 minus log of 100. So this becomes minus log of 100. Right? So this is the lower bound. So P of X has a lower bound, which is this value. Okay. So sorry, the P of X, we need to, this is A plus B, so it becomes the B, log of B is greater than that. So let's call that generator, so log of P of generator, okay. So again, this is log of A plus B, same thing. And we say that this is always greater than that. Wait, no, I think, again, I did a mistake. That was crap, A plus B, log of P of X. Okay, all right. So, so that's a lower bound that we have. And then we could also define.
How can we say that is the lower bound? Because we don't know the nature of A and B, right?
We do know. We say if A is greater than 0.
Yeah, that is good. Here, the probability, not the probability, sorry.
Which is a lesser value, right?
Which is the lesser one, sorry. Like my formulation.
So here we assume this is the lower one. This is the lesser one. Okay. So where I was.
This is not. I think we can make a conclusion based on that, right? Because what it says log of P of data is smaller than log of P of the generator plus a constant number.
Sorry, wait.
Can we conclude that that will be the absolute lower bound that it will be? It will be the lower bound or not? We are unable to.
It will be the absolute lower one.
What if I go for the other term?
What do you mean by that? Do you mean the P of noise?
Oh yeah, greater than P of.
So that won't be lower bound. That's higher than the other one, right? %99 of the time you say this, 1% of the time you say that. 99% of the time that's the highest value. So that 1% becomes the lowest value.
Right? Yes.
Okay. So we are solving it for this example, right?
You want to show this is problematic, right?
Yes.
You want to show it's problematic, right?
Yeah. You guys got. All right. Let me see. That's correct. So this is correct. So this, we are basically saying that this log of this data is always greater than that. That's the lower bound. Okay. Now let's define an upper bound. What's the upper bound for this solution? So the log of p of x. Okay. So instead of p of x, also this we can just define this as our generator, because this total is your generative model, right? The model that 1% of time produces this, 99% of produces that, right? So I'm going to put a g here, just so we understand. That's log of over your generator, basically. So in the higher case, basically, this is greater than log of let me see. Lower bound. Fine, something. Yeah, so there's something I'm missing. The expectation. So this is the log greater than that. So expectation of log of x is greater than expectation of this term. Expectation of log of theta x minus log 100. So that becomes the lower with the expectation. So now we want an upper bound, and the idea of upper bound is that, well, this is the lower bound. Upper bound becomes this p of theta, like the scenario that's the highest value that can. It becomes this expectation is larger than this expectation, right? So the upper bound basically says that expected value of log p theta x is greater than expected value of log pg x, our generator. Okay, so that becomes the lower bound, like the highest basically scenario that you could get.
Sorry. It will be equal because that is contradictory.
Why should be? So this is the, on a lower bound, in normal scenario, you always have this that is higher than that.
Yes.
Okay. So there is a scenario that this could be higher than that. Comes in the upper bound scenario. That just becomes on the lower bound, it becomes the highest value that you can achieve. Okay. So if we use equal, then you say that the highest amount that you can reach, yeah, it could
Equal to.
could be upper bound to be equal. That's a good point.
Because
So
logically, generator can't go over data itself, right? Like that's why it is the expectation value should be equal at the upper bound.
well, not logically, because you don't know p of data. Normally, you don't have it. You only have samples, right?
That's
Okay. So now find the upper bound minus the lower bound. The difference between upper bound and the lower bound will be technically this minus this becomes log 100, right? So it's log 100. So the gap in between a model that's all noise, technically fully noise, really low as possible, and the gap between the model is like a perfect generator is log 100, correct? That doesn't make sense? So that's again, this is a scenario where you always produce a noise technically, right? The probability of giving data is technically 1% only. Like the worst case scenario. This is a scenario that you have a perfect model. It gives the gap between these two is always log 100. Now, if let's look at something like a relative basically error or a relative ratio between the models. So log 100 is the gap, this region, right? And then we can put on the denominator expected value of log P of theta X. This ratio basically can tell you that for any data point X, you can calculate what's the ratio between what your model is producing and what's that basically gap between the upper and lower bound. Okay. Now, this term on the denominator is fixed, but if you think about denominator, P of X, if X is a data point that you're providing, right? If your data, the dimension, like say this is the dimension of your data increases, okay? The more dimension you have in your data, the more complex this data gets. What do you think will happen on the denominator? That P of data, technically, ignore the log and expectation. The P of data goes down. The more data that you have, the more dimension that you have, if you pass that data to a probability, the chance of belonging becomes really low because it becomes such a basically high dimensional data. So if the more dimension you have, the P of data over that point goes down. That's basically what happens. So like you become like a really high dimensional data. So that basically tells you that as I add more dimension to this calculation that we have, if I want to look at this ratio, so this ratio there's a constant log divided by this value. P of data probability. What's the maximum value it can get? It can go to 1, right? So, and here, most of the time when you increase the dimension, what happens to this? Goes down, P of data. So when P of data goes down, what happens to log? Log goes up in a negative direction, right? So the higher basically this, the higher the dimension, the denominator increases, right? The ratio between this and the denominator, what happened? Becomes smaller, correct? So it becomes smaller. On the other end, when the dimension is like a probability is higher, this becomes larger. So if you think about from perspective of learning, using maximum likelihood with a model that almost all the time produces noise, when you add more dimension, this relationship is actually ends up becomes smaller in compared to this one. So you could have a model that 99% of the time it produces noise, but using likelihood learning, that becomes a good model. Because it's just basically what this is like. If you think about it from the relationship between upper bound for the best model and lower bound, the gap between those two, that this relational basically tells you that for a given data point, for example, if I compare it with the best case and worst case scenario, what will happen? Like how good is that model? The more dimension that you have, it basically tells you that it's good, right? However, it's not good. It's almost 99% of the time is noise. So that is one of the problem with likelihood learning. In a higher dimensional data, it's possible that you get a good likelihood, but you're actually not learning, technically learning anything. And again, this is just a simple model of 99% just always print noise, basically. The other problem with likelihood is if you just mimicking the data, like memorizing the data, you will get a large likelihood, but you don't produce anything. Like if you ask the model again to produce, it overfitted to the data. So likelihood, Linux has that issue. If you just focus on the likelihood, the model can easily just overfit to the data. So these are all becomes a reason that we were like, okay, could we focus on a way that we want to still produce the data, but we want to have a way that we don't focus on the likelihood, because the likelihood is easily could be misleading. Now,
Something doesn't click. That's like when we increase the dimension, P data goes down.
when you increase the dimension, the P data goes down. That's correct. The more dimension that you have when you try to get because think about the search space. The more dimension that you have, the point becomes really rare in that dimension, right? So let's say I have a 1D. This is 1D, and these are all my points. Okay. If I go to 2D, now these are my points, right? If I go to 3D for the same points, let's read it here. How like a wide spread basically that region becomes. The more dimension you add, the points becomes really far, right? So the likelihood of a data becomes really low, the probability of that data. So yeah, I mean, that makes sense, because it just becomes harder to validate a point technically.
It's become harder, but P data is the actual representation of the data. So there are some points, like it's just, I mean, it's not that
So you have let's say I have a probability distribution over a large number of columns. It's like I have this multivariate Gaussian or large. When you pass a new data to it, it will tell you that it will give you a really low probability because it's not that likely. Because technically you haven't seen everything.
But P data has seen everything.
No, you don't have P data. The whole thing about this class is that we never have P data.
But we're talking about P data.
Yes, technically think about the sample that you have. You never have full P data. You have sample data technically, right? So if it's like having a P data, that means that you actually found the probability distribution of generating something, right? Go back again here. Probability of X. When we go to all the models that we saw before, you need to, on like variational autoencoders and others, you need to basically have this untraceable integration over all possible Z to produce probability of X, because we don't have probability of X. We need to generate it. Data also is like here, is like you don't technically have P of data, right? You have the sample over that, and you basically respond with respect to that, right? But even if you have some assumption or some basic understanding of your P of data, that doesn't mean if you pass a data point to it, it will give you a high probability, right?
But if it's a good data, real data,
Okay.
it gives
That becomes assumption. That's not realistic, right? You're saying that under some assumption, I have the perfect probability of data, right? Tell me about curse of dimensionality. When you add one column, how many data points do you need to learn it? Exponential, right? Every time you add a new dimension, you need exponential more data to learn it.
The only issue that I have is that we are not talking about PG of X. We are talking about P data of X, and P data of X, I think, should not be a function of D. Because P data, it's like, it's that real function that we cannot find it in a real scenario, right? And that has, it doesn't matter how many dimensions you have. It's just a probability distribution. Sometimes it's
let's say I have this table has 3 columns, right? Height, weight, BMI. And I say this is multivariate Gaussian, correct? And I fit the distribution tree and I learn it. Then I add 100 more columns to it. Okay. What you're saying is that doesn't matter how many columns I add, this I will learn it. because I have the data. Correct? That's not always learnable.
But you just said what I said, right? But can I
Yes.
say what you said?
Yes.
But what you say, at least how I hear it, is that if we have the p data of x, if we increase the d, p data of x decreases.
No. I don't say if you have P of data and you increase the dimension, because that's not the same distribution anymore. The more dimension you have, even if you have that P of data, the probability that P of data for that data set produces is low. The chance of having data in a higher dimension becomes lower by default.
All of them all together.
Yeah.
All the dimensions.
Like all dimension. I'm not talking about you have a P of data, now you added one new columns. No, just overall scenario. That now makes sense. Okay. Now the idea here in GAN is that, okay, we want to have this scenario that I have this distribution S1, like images, and I have this other distribution S2. So data X, and this could be a generator. And our goal is that to compare these two distributions without a need to have a likelihood learning. And that becomes the whole idea behind GAN that, well, an easy way for us to compare two distributions is some sort of like a test, like a statistical test, right? For comparison. Like if you have two population and you have two samples and you want to compare them to see if they're coming from same basically population, or they are basically similar. So that's the idea here. Instead of we trying to learn the maximum likelihood, let's use some statistical tests to compare two distributions and see that if these two distributions are similar. Okay, so now one of the techniques that basically for two sample tests we can use is like going to be like a t-test. And the idea will be you have some null hypothesis that these two are coming, they're similar or they are not similar. And in t-test, you can use different basically modality, or you can use mean, variance, like mean, mode, or like depending on what you're looking for. But that becomes something like this, for example, for samples from one of them, you find the mean minus the mean from the other ones, and then divided by basically this ratio of the standard deviation or variances. You get some t values, and you compare it with that basically alpha that you have if you either approve or basically reject the null hypothesis, right? And this idea becomes like a likelihood free, because now you don't need to train based on the likelihood. You just need to train based on the t-test between two sample data to see that if they are coming from same distribution. And what could be the goal of learning here? Because if you think about from generative perspective, what's the goal that we have? We want a model that can generate good quality data. And you want this model to be in this level that the data that it generates, if you compare it as like a t-test, like some sort of two-sided test, with the actual data that you had for training, they're not basically indistinguishable. You cannot basically separate those from each other. They kind of like look alike. So that becomes the idea of what we want to do with GAN. So we basically have, again, two, like S1 that becomes your P of data. This is it, samples for Ashkan reference. And then you have this generator. This is like a Z. And we're going to basically come up with some sort of alternative to measures the distinguishable or basically separation between these two sets of data or samples that you have. Well, there are challenges with this, with comparing this like a distributions, and they are not like that straightforward. For example, here on the left you have these two Gaussian, and you're trying to compare those, or it could be something like this. It could be one becomes actually a Gaussian, one is a Cauchy. It's like they are not basically the same. So just simply comparison based on mean, you might get perfect result here, but they are not same distribution technically, right? So it's kind of like something to keep in mind. Now, the one of the ways to improve that that separation is, instead of maybe we do actually like a t-test and stuff like that, like a statistical test, we use neural network. So instead of we defined as test, just define a neural network that its job is to give us like the separation between these two. Tells us how similar or how basically dissimilar these two are. And that becomes the idea of discriminator neural network or basically model in the GAN. So GAN has this generative model that we will see, and it has a discriminative. The generative, similar to other ones, its job is to generate images. Fake image basically look realistic. You have this discriminator, which its job is to compare the image generated by GAN with the data that you actually have and tell you that if they are similar or not. Basically, it's kind of like a spam detector. Its job is that to say that which one are fake, which one is real. That's the discriminator. Generator job is to create images. The goal here is that this we will see that it's kind of like a two players game. One of them is generator, tries to generate image that's really good quality. Then there is another one that's calling like the bluff, like it's like if it's fake or if it's real. The generator then basically the discriminator first calls out, and based on the result, if it was correct or not, it updates its own learning. But then the generator also learns something. It says, okay, my goal is that to basically win this game, right? So I want to also next time to create an image that you are not able to distinguish it. So it becomes a min-max game technically. One of them is focusing on basically maximizing the separation. One of them is focusing on minimizing the ratio or the rate of detection. Like I want to build my images somehow that you're not able to find it, but the other one is focused that I want to separate images. So both of them, we want to update them at the same time together. So one becomes good as generation, one becomes good as discrimination. So that becomes the idea instead of using the t-test, for example. So here, what we do, we're going to define G again as our generator. Generator gets a Z, some latent, and has some parameters theta. It generates some image. So this X with the asterisk is like a generated image. Then we have this discriminator model, as we showed with F, and it's like a parameter phi. And that's job is that it gets two images. It gets X like asterisk and actually real image X, and it tells you which one is fake, which one is basically real. So, any questions so far? Now, the way that this, what you see here is that on the left, so let's start with this like a scenario of 1D. On the left, you have the red arrows, those are the generated images, like the generated data synthesized. And on the cyan arrows, those are the real data. So at first, on image A, you have theta is by default 0.3, so the model is pretty bad. And as you can see, they are really disjoint from each other, whatever the generated built versus the real. And for discriminator, it's pretty easy to separate those. So this line that you see is just basically some sort of like a sigmoid line. Like it separates perfectly on 0.5 both classes from each other. Then in the next iteration, the generator updates its parameters and it basically generates new data. So now the data came to the right becomes a bit more similar to the new ones. Now the discriminator still has some sort of like a capabilities of separating from each other. A couple of iterations later, it gets to the point that the generator is creating images that are really look alike from the real data, and the discriminator now it has a hard time to detect it. And if you see here on the image, this part of the curve is look like this part basically. And in a basically, if you think about in a sigmoid, that is the belly of the sigmoid is where the model is not sure technically. Like if you think about how sigmoid looks like if you have something like that, this region is technically something that you are not sure because the probability is between, for example, 0.4 or 0.6. That's a region that normally model is not sure, and you define that threshold anyway. So this is that region, and we don't see. So that means the discriminator has a hard time distinguishing this from each other. Okay. So, any question on that? So
Theta is just some score, is there a?
theta is is parameter of the network. Sorry, so let me, here, we have it here. So when we see G of theta, that means the generator is a neural network with parameterized theta. Discriminator with parameters phi is, and it's not one parameter, it's set of, right? It's like a neural network with the parameters. So here the idea is that we have this two-player min-max game, which generator is trying to minimize, discriminator is trying to maximize this value. Okay, and this is the direction. So what you see in the picture from for the generator, it goes from Z to X. For the discriminator, it goes from X to Y, because it's kind of like this is what it means basically is a classification. Y is the label, real, fake, and you try to this model to learn to map this to that basically. That's what it's basically referring to. Then. So if you think about the generator overall, it gets a sample. From that sample, basically generates some images, and it's similar to the flow model. But here we don't need. It doesn't need to be invertible, so we don't care about the inversion in GAN. Also, P of GX is implicit, so we don't have likelihood. So like other models, VAE or GAN, we don't need to learn probabilities of the data, like probability of over Z. It's just implicit. And our goal is that to minimize some sort of like a separation between real data and generated data. But instead of using the two sample tests, we're actually using a neural network technically, okay, which is the discriminator. On the other hand, discriminator is like a binary classifier that does real versus fake. If you have, and the test statistic, which is the result of that discriminator, if you have a low loss, that means real, and so low loss from the discrimination, that means real and fake are easy to distinguish. If you have a high loss, that means real and fake are hard to distinguish from each other, okay? So if you put it all together, this is basically how you can look at the GAN. So there is some latent variable that we sample from Z, some Gaussian, and then goes to a generator with parameters theta. This will generate an image. Then you bring a real actual image and you pass those two together to a discriminator, which is a function over the whatever image it comes. And it's sigmoid because it's like a binary classification. And it basically gives you something like that, right? Because here we do sigmoid, so we have a basically log loss, cost function. So this log loss basically has two parts. The first, let's start with the second part. So, so the second part of this log loss is only focusing on f. If you see, is f over xi. What is xi? Actual image. So log over sigmoid of this. So you pass a real image to the discriminator, and you ask it, is it real or fake? And it gives you a probability based on the is a sigmoid. If the probability is high, that means is a real data. The model should be able to say it's real. If the probability is high, the log goes towards zero, correct? If the log goes towards zero, this becomes almost zero. So for discriminator, goal is to give a high sigmoid value to real images in order to make this loss zero. Does that make sense? Then for the first part is 1 minus whatever discriminator predicts for the fake images. We want that also to go to zero. The only way this goes to zero is if this is 1 minus 0 technically, right? So that means discriminator's goal is for fake images to give a lowest possible probability, if it's from the binary classification perspective, right? So high probability for real, fake for this ones. So, and the goal for discriminator is to minimize that. Now, if you think about the generative model uses the same thing, only the first part. This, the first part. So generative model is focusing on increasing this value, increasing the negative of this value, okay? That means, or if you look at it from the positive perspective, that means the generative wants to create image somehow that this sigmoid value is high. That means the discriminator is doing a bad job in figuring it out. So that's why it's if you think about like this, becomes 1 minus some let's say the probability is higher, so this goes toward becomes smaller and smaller. So the log becomes larger and larger in negative side, right? So this becomes a large negative value. If you basically able to basically let's call it deceive the discriminator, and that comes back to here when you see there's a min max. So if you think about generator goal is to minimize what this. The only way this gets minimized if this value gets a high probability. If this gets a low probability, this actually goes to 0. It has a cap, right? So this is a log over the p. We know that if you think about this, and this is the p, so this is 1 and this is minus infinite. If the discriminator does a really good job in figuring it out and says this is really low chance, then the difference between that 1 minus sigmoid comes around this region. So your log of that becomes almost 0. But if the discriminative does a bad job in figuring out the fake, then you get 1 minus something, you come in this region and you get something really large in negative. So, and that becomes the goal for generative, is to minimize this value. So minimization here is negative. For discriminative, because it was min-max, the goal was maximization. That's why we have a negative behind this. So our goal here is to maximize that term above. And the only way you can maximize it is if the first term becomes log of 0, the second term becomes log of 1, and the second term becomes also log of 1. Correct? Question on that? All right. So now if we think about from the objective perspective, so we are going to first start with respect to discriminator, because remember this is like a two players game, so they are basically working separate. So let's look at it from the perspective of discriminator. So which the goal was to maximize that term. But this is the same log error that you saw in the image. So our goal is to maximize this with respect to this parameter. So there are so inside whatever you see actually in here sigmoid over something. It's possible that if you see that later in other slides, instead of that I just wrote this, because that sigmoid is technically the discriminator. So instead of that, if you see a D term, that means the same thing. So here basically, in order to solve this, well, you could just do batch approximation. So you sample S1 data point and calculate that term, and then you calculate this term. Instead of expectation, becomes some basically like a Monte Carlo basically sampling. So then we can formulate the loss. Basically, our goal is to minimize, this becomes the negative of that. This was maximization. We wrote it in a negative side to make it minimization. So this becomes to minimize this term. Now, let's say you have a fixed generator, because the idea is that you have a generator, it generates data, and then discriminator works. So the generator is fixed. If your discriminator assigns a p equal 1 to true data, that becomes a good discriminator, and assigns a p equals 0 to fake data, that becomes a perfect scenario, right? So that basically introduced an idea for us, an optimal discriminator. What's the definition of, like, we will be a discriminator that can separate all the fake and real images. So we have this loss, which we can write it as basically P of theta x times discriminator over x minus P of theta x times log of, there's a log here, sorry, log of discriminator. I'm going to show you where this comes from. Log of 1 minus discriminator for x. So this comes from the first equation that you see. So this is an expectation. So I just brought the P of theta inside the expectation. P of theta times this log, right? Minus, plus, this should be plus, P of theta times this log. And instead of sigmoid, I just wrote D of, it means the discriminator. Again, this term, sigmoid, is the same as discriminator. This term, sigmoid, is the same as discriminator.
Those expectations are over different distributions.
So over Z and G, the X, that's a great catch. So think about this. When you, what you see here says Z with respect to Z, right? What does that mean? You sample a point Z, you pass the Z to G, correct? And it will produce a point. Doesn't matter what you call that point. Y, X, P, right? So from the discriminator perspective, it doesn't care if it's Z or X prime, it receives point. So you can write it with just with respect to same variable. Because discriminative, it gets X as an input, maps X to Y. X could be real, could be fake. Does that make sense? So again, think about this. So
Can be PGX instead of P data X? I don't know, like
PG,
X, like just the second term on the right side.
yeah, this is PG, right? Data that comes from the generator. Correct, you're right. But the inside parameter, this becomes X because discriminator again doesn't care if it's X or Z. So this is your loss function, and we want to find optimal discriminator. So if you just take a derivation of this with respect to the discriminator, right, and set it to 0. So you basically get P of theta X over D, this is plus, D of phi X, and this becomes, there's a negative here, minus P of G X 1 minus D phi X, correct? Set this to 0 or just like this two equal. And we want to find D of phi, so D of phi X. This two term will have, and this term will have, so this becomes, if I put a star, P of theta X over P of theta X plus P of G X, right? If we just do the cross multiplication and keep D of theta on one side, that's basically what it comes out. So this is the optimal discriminator, right? So because it took a derivation, set it to 0, like to minimize. The discriminator that minimizes that loss, basically. Okay. Does that make sense? Your goal is to minimize the loss. The only unknown you have here is D. So in order, convex, if you want to minimize what you do, take a derivation with respect to D. That becomes the optimal value for D, which is this equation. Now, if your, now think about the data. Now, if your generator is pretty good, it generates a data that is identical to the P of data, then this loss becomes 1/2, right? And what does that mean, this loss is 1/2? From discriminative perspective, discriminative is a sigmoid. 1/2 means 0.5. That means this discriminative always says, I don't know technically. The sigmoid is basically the value is always 0.5. 50% class 1, 50% class 0. So under the perfect scenario, perfect generative model, a model that P of theta and P of x are the same, the optimal discriminative model will produce 0.5. It's incapable of separating. That means you're able to fool the discriminative model. Now, let me finish this slide and we take a break. So what we want to do, we pick that definition for the optimal discriminator and replace it back in the formula that we had. So instead of that log over discriminator, I just put this as a discriminator. Okay. Now, this basically going to introduce something called, we're going to basically map this something called Jensen-Shannon basically divergence. It's a metric for like similar to Kähler divergence to compare two basically distribution. One of the differences is that it's symmetric. So Kähler divergence is non-symmetric, but Jensen-Shannon is basically symmetric. Yes.
In that, when you replace this new thing into the original equation, shouldn't the second term have log of 1 minus that term?
No, that's the discriminator.
1 minus is the discriminator.
Think about the discriminator. In a binary classification, for class here, if you see here, for the class 1, this is the discriminator.
Okay.
For class 0 is 1 minus that. It's the discriminator.
Okay.
You always respond with respect to class 1, right? So that's the same thing.
Okay.
We use also, if you think about it here, we use 1 minus in order to reach to that basically. So that becomes your optimal discriminator. There's a difference actually if in the formula also. So the first one is P of data.
Okay.
This is P of G. So think about it, 1 minus the other one, P of G. So now look at the objective function here, and we want to see how did we reach to this equation minus log 4. So what we basically, if you think about this term, what we can do, so Jensen-Shannon divergence basically requires this, if you are basically calculating, if this was insert of like a Kähler or Jensen-Kähler between P of Q or what you call it here, P of data, and this is what we want is like a P of average. We need some sort of like an average average distances here. So the average between P of G and P of data. So that's why in the denominator we want to divide by 2 this to become an average error, basically average value. But when you add it over 2 in the denominator, technically that means we did have 2, I'm just going to write it for one of those. So think about that term that you have, log P of data x over P of data x plus P of G x, okay? What I want to do, I want to bring this over here. In order to do that, this is similar of having 2 times this here, technically, correct? So this 2 will come out as log of basically, because it was in the denominator, technically, if you bring it up, becomes minus log 2. So you have minus log 2 for the left term, and you have minus log 2 for the right term. Together becomes minus log 4 over there. Okay, so that's where we got this minus log. Now this converts this to 2 times Jensen-Shannon minus log 4. Okay, that becomes the loss function that we have here, simplified version of it. Okay, let's take a short break here. And then continue. Let's go. Where were we? So we were here. So we defined this basically Jensen-Shannon divergence. And we're going to review the idea of the Jensen-Shannon divergence. So Jensen divergence has 2 terms. If you look at the equation, there are 2 terms. the term on the left and the term on the right, basically, and minus that log 4. Now, the term on the left, basically, it focuses on P of data. And that basically defines something called coverage. The term on the right, which P of G was on top, on the denominator, that focuses on quality. When you work on coverage, which is this region, your goal is that to cover all the region that the data comes from, actually. That means you have learned that. Like I can cover all the space that image comes from. When you focus on the second one, the quality, that's the quality of the data that you are generating. So if my data, actual data comes from this distribution, my image data, generated data comes from this distribution, this is the two different errors. I have this error area under this, which is going to be quality. Why? Because I have built images that's not from original distribution, bad quality. If you have this one high, that means you have built basically, you have this data that's covered, but it's kind of like you don't have any data generated from that coverage area. What you want in Jensen equality is that these two to overlap on top of each other. That becomes a perfect, basically, perfect value that you have. Now, if you're looking at the equation now again, so we have this this distance, Jensen distance, basically. There's a Keil divergence between this and Keil divergence between that. So the second term, as you can see, is the average, that average basically value. And you basically average these two Keils, so it becomes one distance. So that becomes the Jensen overall. So it's two Keil values averaged together and becomes Jensen and is always positive. It's only 0 if P and Q are equal, and it's symmetric. And if you put a square root over that, it basically called Jensen-Shannon distance. Okay. So again, under the optimal scenario, we saw that Jensen distance becomes minus log 4. And then this was the overall the generator that we have. Let's go here. So we also saw this. So this, again, just a refresher. So the total loss function was this mean max, and then this plus the negative of the log. This is a phi parameter. That means the discriminator. This is theta. That means the generator. So there are two different, basically, training loss. Now, the idea will be something like this. So you draw a sample. Basically, you have this batch data X, and then you draw a random sample noise from Z, and you generate a fake image. You bring the fake image, pass it to the discriminator. Discriminator makes a decision. You update the loss of the discriminator by taking gradient, like a gradient, update the parameter phi. And then after you update the discriminator, you go update the generator using a portion of the discriminator loss, which is the portion that the generator wants to produce high quality. And you repeat that for a series of time. Okay. So the learning process is straightforward. It's just kind of like a 2 steps basically learning. And what will happen here is that if you think about the loss perspective, these two are fighting with each other technically, right? So the generator is the red loss. At first is really high because your quality of the images are bad. Then over time, the generator loss goes down. When the generator loss passes this corner, the discriminator loss goes up. Because now that's the point that the generator is doing a great job and discriminator is not able to separate those from each other. Okay, so discriminator loss for the real data is that. This comes from the same equation. For fake data is that part, and generator loss is this value overall. So it's like you have 3 components in the same loss function. Okay. The loss for the real data is small if you give a high, basically probability to a real data. That basically becomes high. The loss for the fake data is small if the probability that discriminator give to it is low. This is LG basically for generator is small if this one gets a high probability technically. So you see they're kind of like working the opposite of each other. Now, this is summarizing the same thing that we just talked about. We have a better image for that here. Yeah, okay. So now this is what technically this alternative alternation happens between the generator and discriminator. So what you see on the image on the left, A, there's X. X is the basically the dotted distribution. The dotted black distribution is X. Then you have Z sampled basically from this space, and this is your Z. And the green is the distribution over Z here. Okay, so this green line is distribution over points that you sampled from Z. Okay, and again, samples are those arrows that we see. So here, this is Z, we sampled, went to a generator, produces some data, they're landing here. This green line is a distribution over that data. And the dotted black line is a distribution over actual images. And then you have this discriminator, which is at first not trained, basically. It's basically, this is your discriminator, and it does the separation. You do one epoch, for example, and the discriminator basically becomes perfect in separating fake from real. Then you go apply the same knowledge to the generator and says that, okay, update your parameter, and now this generator generates another set of images, and they are closer to the distribution of the black dot, the real data. And this back and forth continues. It basically gets to this point that the generator produces image that falls over the real data distribution. And when that's the case, the discriminator just always gives 0.5 because it cannot separate this from each other. So these are like, for example, these are examples that GAN has generated. And as you can see on the bottom, the quality of the generation for GANs from 2014 up to we have here 2021 has increased by a lot, right? So it just becomes they become really good. They have basically successfully applied, but there are some challenges, or significant challenges that GANs has. One of them is unstable optimization. One of the problem that GAN has is vanishing gradients. I'm going to talk about why it suffers from that. There is another one, it's really common, it's called mode collapse. And mode collapse is the scenario of, if you think about from the concept of the image. So let's say I'm trying to learn to produce images. And then I have images of different items. And if you think about from model perspective, model need to learn, build a car, build a bike, build a shoe or whatever, like as an image. Mode collapse is a scenario where your model only produces most of the time, produces only one of those items. Every time you sample, it just gives same car. That's the idea of mode collapse, basically. It's incapable of generating more. And then the other one is basically evaluation. And here it's like we don't actually know how to evaluate GANs properly. There's no standardized way of evaluating GANs. And these are all causing problems because makes GANs training is challenging. You know, it's as I said, it's not a really easy algorithm to train. Now, there's some basically optimization that happens for GAN, but there is some theorem that's behind all of this. It's kind of like informal. And the theorem basically says that if the generator updates is done in function space and discriminator is at every step. Discriminator updates every step and generator basically updates once in a while. For example, the generator is guaranteed to generate perfect data. That's really optimistic. It's kind of like it doesn't happen. It's like an unrealistic assumption. There are some practical implication or basically observation that we have seen that you need to take in order to make GANs actually perform nice. They normally often show this oscillatory basically behavior, which we're going to show that comes around that vanishing gradient concept. But this is the idea of mode collapse. As you see, the model produces a lot of the same image. You know, it's kind of like this image repeats a lot when you sample from this model. That means normally that means something like a mode collapse. Another way of mode collapse is something like this. So if you have a target distribution that you are trying to learn on top, it's like a mixture, basically mixture of Gaussian, let's say. Okay, so you try to learn all of those distributions together. Mode collapse is a scenario that your model always only learn one of those. So as the step goes, doesn't matter how many times you iterate, the model goes to the next one, but it forgets the previous one. So that's one of the challenges that GANs has. It's called mode collapse. And this is another example of the mode collapse. Like it always either produce one digit or similar to a digit. So there is this here for practical tips goes to this page, this repo. It's pretty popular. So it has practical basically advices for GANs based on all the papers being published and overall what people do in industry and academy. So if you are trying to use GAN, I highly recommend you to technically take a look at this Git repo. This is what it's called, GAN hacks. Basically, that's the name of the repo. If you're again working with GANs, just definitely review that. So now, okay, now so the thing here is that we talked about this tail divergence concept, and we also introduced the Jensen-Shannon divergence, which is a scaled and shift version of the Kale divergence. But what we want to do here is that instead of using Kale divergence or Shannon divergence, basically we want to introduce a new types of basically divergence. Why? Because so Shannon divergence. I thought we had an image. Yeah, I can actually talk on this. The problem with this type of, like for example, Shannon divergence is that vanishing gradients happens, and that vanishing gradient, if you look at the image, so when you get to the point that either it's possible you're on the point that, let's say I have this data, my real data and my fake data. They're easily distinguishable. And your discriminator separates those perfectly. So if you have a scenario like that, what happens is when you do back propagation, because the discriminator did a great job, the gradients are almost zero, right? So the gradients will vanish. So in the next iteration, there is no learning happening. Right, so basically, you cannot update anything. Your generator cannot improve itself. Or even in this scenario here, it gets to the point that discriminator cannot do anything because the gradients are pretty small. So it basically ends up having vanishing gradients issues. So those are challenges that we get with Shannon, for example. Now, the solution here is that, well, let's, instead of Shannon divergence, use something else called F divergence, basically. Okay, so F divergence, it's a new types of basically divergence that we're going to learn today. And in the Kale divergence or Shannon divergence, you had this expectation over, and you had P of X, Q of X in Kale. So in Kale, you didn't have this F behind. That's Kale divergence, right? In F divergence, you have this function F that basically sits behind that value. And this function F, it should be some divergence function that has series of properties. One, it should be basically convex with like a lower semi-continuous convex function. And it should have a value of 0 if the probability inside is 1. So at F1 should be 0. Should be a function that at 0.1, similar to log, is produce zero, it should be convex and it should be lower semi-continuous. Okay. So if you think about a continuous function, basically a continuous function is a function that if you have a variable x around the point, so let's say if I change x around a point by some value, so that point, let's say C is my actual point, and I can have another data point around C. The difference between these two, okay, the difference between these two in a positive way, if it's less than something like that, then the difference between this is also something small. So continuous function means that if you change a variable by a small amount, the impact in the function of that variable is also going to be a small amount. That becomes continuous. Now, on the other end, when we talk about this lower semi-continuous, it's in the image way here, a simple way, is anytime a function doesn't have abrupt jump down, right? It becomes like a semi-continuous. But the I think we have that we're going to go. I'm going to prove it somehow on that paper, on that image we have later. But so that this becomes an example of semi-continuous, for example. So you need to find a function f which is semi-continuous at point 1 produces 0 and is convex. Then you can use that in your Kähler divergence by assigning it here. So this way, this becomes F divergence. Now you have the freedom technique. The idea here is that instead of you only focusing on Kähler divergence or Shannon, you have the freedom to use any function for finding the dissimilarity or the distance between these two, P of Q, right? The only basically like a limitation or constraint is that whatever function that you pick should be convex, at point 1 should produce 0 and should be lower semi-continuous. Okay, then that becomes F divergence. Now, for Jensen inequality, we have seen this before. Expectation of a basically a function of something is always greater than a function of that expectation, right? We saw this for expectation of log. So using the same thing, we basically reach to this will be equal to F1, which becomes F1 is 0. That means the minimum value this function will produce is also 0. That's just a proof for the minimum value. Now, lower semi-continuity technically, basically it says that if you have a function, this function, limit inferior means if you pick the minimum across all the possibilities, that becomes the limit inferior. So basically we say that limit inferior over this function as we approach it is always should be less than this. Okay, this should be less than this value. That definition makes a function semi-continued. That means it's always behaved in the way that we expect. When you approach it, it's always lower than that. It's like this kind of like a lower value. It doesn't have an abrupt change, and this is an example. So the one on the left is lower semi-continuous. It's because it behaves basically is convex, and it behaves like for every point. If you pick this point, as you approach it, is always lower. But this one is not because there's this abrupt jump down. Now, this point and this point, the values are not valid with respect to what we say as like it should be always lower than the other one. Okay, so if you have abrupt jump like this, it's no longer semi-continued. If it's just it's like a normal, basically, and like it doesn't have that abruption, then it becomes and it's convex, then it becomes lower semi-continued. So these are example of F divergence that you can basically use. So as you can see, for most of this basically distances, you already have the basic F divergence formula for that. So if you, for example, if you are using Kähler divergence, Px log this value, in basically F divergence version of it becomes U log U. Okay, so these are like, we don't want to prove this in this class, but these are like a basically proved value. So now the idea here will be that, so we want to basically, we need to basically calculate this value, depending on, because this D of F here basically is not like a Shannon, it's not symmetric. So D of F, P of theta, versus D of F, P of theta, P of theta, they're like a different. So you calculate two different divergence, F divergence. The challenge with both of this is still is that you need to have this ratio in order to calculate this P of theta, right? And that ratio is similar to everything that we have seen so far. Depends on P of theta and P of theta, which most of the time we don't know that, we don't have those. Like that's the challenge with most of these algorithms, that we don't have P of theta, we don't have P of theta. And this divergence requires that ratio, okay? So the idea here was that, okay, if that ratio is, it's basically unknown, what could we do? Basically, we can rewrite this F divergence, maybe using some neural network to find that ratio for us, instead of we try to estimate it. So, does that make sense so far? So we introduced this F function instead of the Shannon or basically KL divergence, which is a convex function, has a minimum at minimum, at 1 will produce 0, and it's semi-continued. It doesn't have any abrupt jump. Then what we say about this is that because this function requires this, basically requires this ratio, which we don't have, we're going to rewrite it so we get rid of this ratio inside. Okay. Now, what we are going to now talk about is a concept called Fenton conjugate. Okay, so basically the Fenton conjugate basically says that if you have a function f, you can find its convex conjugate. Okay, you can find its convex conjugate as follows. So let's say we have this function f, and f could get any variable. You rewrite the convex conjugate of it as f star t with respect to some t equals supreme of a linear combination minus fu. Okay, so I'm going to talk about this. So we have f star t equal a supreme over t come from the domain of f ut minus fu. Okay, so basically what it says that any function, I can write it as some sort of like a convex conjugate for that function. And in order to do that, basically I introduce this t. T is like it could be a set of functions, could be just here a variable. Okay. Supreme, so it means maximum possible, basically supreme. So when we say supreme of t that comes from this domain, that means across all possible t that comes from this domain, the one that gives you the maximum, like the value. So this is the definition of supreme. So what we are saying is that this convex conjugate of that f function equal to technically maximum of this for all possible t. And you have this ut, which is a linear combination. So there's a u, there's a linear combination of over t. You are solving with respect to t. U is fixed here because you solve with respect to t. Minus the function over u, the original function. So we have this function. We say that, well, and this function, for example, gets, let's say, gets u. And we say that we want to write a conjugate, for convex conjugate for that. We write it with respect to another variable t, and we use this equation. Okay, that's the convex conjugate. Does it make sense so far? So it's just some sort of like a change of variable, but change of formula to a convex, basically. Now, so when we say t is the supreme of this, that means I can basically say T star equal argmax over UT minus FU. Okay. So this becomes the argmax. Sorry, we solve it in the under here. No, usually we write this. We wrote this with respect to U. Just want to match you whatever you have on the board. So with respect to solve it with respect to U. And that's FU. Okay. So this becomes U that basically argmaxes this variable, and this becomes U star also. T star, U star, whatever you want to call it. Okay. We say that we solve this value equal the maximum of this, supreme of this, right? And supreme of this happens from one U. There's a U that's going to make this maximum, right? That U is equal argmax of this, correct? Does that make sense? So we call that U here U star with T star, and then we replaced it in the equation in this equation. So instead of I want to get rid of that supreme. So basically we rewrite this as UT minus FU, and instead of U, because it was supposed to be the supreme, you just put this T star F T star. Okay, so that's what how we replace U with the, and we got rid of the supreme term. Okay, now so what are the properties? So F star or F asterisk is the convex and lower semi-continuous. So it's convex and lower semi-continuous. It has this Fenton conjugate properties that F star a star. That means if you do a second, it's kind of like a reverse. If you do a reverse convex conjugate on this, it should go back to F. It should give you back the original F basically. Okay, that's the property that you have. And me the file. So I'm just okay, I'm not going to go over it, but I have uploaded 2 examples for this, for you to basically try it out yourself. So let's say we have this function f of x. It's so small. But of the ratio, it doesn't. Okay, so let's say we have this function f of x equal 1 over 2x2. That's just the function that we have. And then we want to basically calculate the conjugate, convex conjugate for that using the equation that you see over there with respect to another variable, y, t, whatever. F star y equal supreme yx minus 1 over 2x2. Okay. Now what you see here, there are 2 terms again. There's this linear term, and this is this basically the original function that we have over there. If we solve it with respect to x, by taking a derivation with respect to x, set it to 0, you get x equal to y. The plot that you see here, the black curve is the original function. These lines that you see is that linear term, x times y, for different x, different y's, basically. So these are the linear. And then when you found x equal to y, so f of y becomes the same thing, 1 over 2 y2, because f of x was 1 over 2 x2. So if x equal to y, f of y becomes 1 over 2 y2. And if you plot that, this is what you will see. So the curve is f of y, the convex conjugate that we found. And that's why we call it supreme, because it's on top of all of those, all the lines below it. Does it make sense? So I will leave this for yourself to solve it. The two questions are here, with the answers also there. But the idea of supreme is that this will be always above anything that basically comes behind, below it. Okay, and then when you go to, there's also this plot for the Fenchel inequality between the two variable x and y and the conversion between those. What you will see here is that the Fenchel inequality basically is zero. This distance is zero only at this range in the center. That's where x and y, they map together perfectly. As soon as you deviate, the gap becomes larger. So the only region that you have this smaller value is when the x and y, they work together in a certain path. Okay, you need to just replace the values in the equation to figure out the zeros. So I leave that for yourself to solve it. The screen again. So that's this part. Then again, if you apply a second time, so now you have this f of t, f of t star is your function. If you apply the second reverse to it, right, it should produce the original function. Okay. And so what we will do here is that in the instead of the function over that value, because we picked some function. So what we did, we basically use that convex conjugate of that function, which becomes a supreme over some t times whatever is the value x minus f prime f star t. Okay, that becomes the reparameterization that we are doing here. Now, so that term that you see, this expectation and over the supreme. So you can bring the supreme outside of the expectation with respect to t. So that's what we are doing here. So we bring the supreme outside. Then if you look at the equation, we go back here. So we have this, we have supreme over t p of x minus f of t. It is expectation here. So we basically break that down. So that gives us expectation over t minus f star t. Now there is a proof also for that in the other document that's uploaded. We don't want to go through that also, but there's a proof for reaching to this calculation. So, but overall, so you get two terms here: txp of x, which is that linear term. Txp of x is the same as this u times t. So it's the linear combination, and then you have this qx f prime or f star. So this is the f star that you have. There is a q multiplication by it. It's just for scaling. Okay, so we have this. It's kind of like a some scaled version of that that's conjugate function, and the first part, the linear, it's just a linear part. The second part is just a penalty term, becomes like a penalty term for deviation. And the another. Yeah. So if you think about the function that the cost that we have, the divergence function that we have on top, we can basically, because when we say this is equal to the supreme, right? Do you agree that we can write it as greater than equal to the supreme? Because supreme is the maximum, right? What's the maximum value? So we say that this is always greater than this. Okay, it's always greater than that. Then from the now overall, what we use here instead of KL divergence, we use F divergence. So this is called F GAN. And in the basically again, the idea will be that you pick any of those F functions that you saw from the table. You decide which one that you want to use. You have again the same thing, discriminator generator. So technically here, T, in case you're wondering what is T, T is the same as D, the discriminator that you have. It's the same neural network that you are using, the same model. So T is that discriminator that you have here. So yeah, actually it says here. T is your discriminator parameterized by phi. We just called it T because we introduced this T star. Okay. Now, if you, in a layman term, if you want to understand what does this, the cost function on top tells you, the divergence tells you that they are all sort of discriminator model T that I could have. When here we see that T could comes from some domain. They're all possible discriminator model that I could develop. Among all of this, I'm looking for a discriminator that gives me the maximum value for this separation. Okay. So this separation, if you think about it, what does this separation tells you then? Expected value generated by the discriminator over the data that comes from the your real data. So if you pass a real image to your discriminator T, if it's a real image, what do you expect to get? High value, high probability. This expected value you're hoping to be high across your real images. The second term, expected value over data that comes from Q. What is Q? Your generator. Data comes from the generator distribution. It's basically the value that you generate for this is F star over the discriminator. That's because that we introduced that F conjugate basically, right? So your goal is that in order to basically, you have this supreme over this term. And this supreme is parameterized by T, and T is your discriminator. Your goal is that to find a discriminator across all this possible discriminator that maximizes the distance between this and this. Because it's supreme, it's a maximization. It's doing a great job of giving a high value to real images, doing a great job of giving a low value to generated images. It's still the same concept of what you saw before, increasing the real image probability, reducing the fake image probability. But we introduce a new function, new way of doing it. And we introduce this basically F function and this F conjugate basically. So the objective function again becomes the same thing, expected value of this minus expected value of this. Okay. Question on that? At this point, no one asks questions. All right. So again, the problem with managing gradient was that when the points are become really easily basically dissimilar or disjoint, right? The generator cannot improve itself because it doesn't get any gradients back. The gradients are always pretty small. It's kind of like a vanishing. So the solution to that is, and there's another types of basically GAN that you will hear, it's called WGAN. And the idea in WGAN is that instead of trying to use divergence methods for separating, we saw Shannon divergence, we saw Kell divergence, we saw F divergence. They're all some sort of like a divergence. So in basically, the idea here is that let's create use some other metric to compare the results. And the technique that we're using called Wasserstein distance, or another term for it is called Earth mover. So Wasserstein's distance or Earth mover, in a layman term, means that if imagine you have a pile of dirt here, and you have another pile of dirt there, and you want to move pile from here to there. Wasserstein distance basically calculates how much effort and energy basically goes from moving this pile to the other pile. And from the concept of this generation, how much effort will it take for us to map generative data basically to real data? That's the idea. So okay. So the Wasserstein distance comes from inferior over this variable, this basically like equation x minus y is like a norm one, and the simpler formula for that is this the distance moving. So it's kind of something like this. So if the when you shift one toward the other one, this requires a lots of movement, gets a higher basically distance. This gets a lower distance because it requires a less amount of effort to move the data. So another example here is that let's say you have these two distribution P and Q. So P is the original data, Q is the data that you're generating. And what we see here is that if x equals 0, P of x is 1. If otherwise it's 0. For the other for the generator, if x equal to theta, it will produce 1. Otherwise, it will produce 0. Okay. So if you want to compare these two distributions using Kähler divergence, if theta equal to 0, that means this is equal to that. This will produce 1. This will produce 1. So the error is 0, the divergence. But as soon as theta is not equal to 0, then this is infinite because you don't know the gap between those two. Then, even for the Jensen-Shannon, the same thing. If theta equal to 0, first one, you get 0. On the second one, we go log 2 because it was minus log, remember, minus log 2. So these are not doing a great job here. On the other hand, for the Wasserstein distance, basically it becomes, remember, it was a norm 1 of x minus y. So it becomes theta, norm 1 of theta minus 0 becomes norm 1 of theta. So that becomes the Wasserstein distance. This is the equation again. On top, norm 1 of x minus y. Now, we're going to look at the easier definition for the Wasserstein distance for discrete variable. So the distance between P and Q comes from some minimization over here. So what you see in this equation, this P here is not a distribution. Okay, this is not. So Pij means amount of, like, how much dirt I need to move from I to J. That becomes Pij. Okay, so this is the amount of basically information that you're moving from one location to the other one. This value, absolute value I minus J, it's the cost. How much effort will it take for me to do that? Okay, so first one is like how much data you're moving, how much dirt you're moving. The second one is that how much effort that movement will take from me. Okay, so you basically calculate this sum across all possibilities, across all ij, and you select the minimum. Basically, you're saying that across all these movements, the one that gives me the minimum, that becomes minimum effort, I will pick that. And we are minimizing this with respect to P, and this is the P. P is something that we minimize with respect. So you want to find an easiest way for transferring one to the other using Wasserstein distance. Now, there are a couple of constraints on this definition. The constraints are around P, because you're solving also with respect to P. P as a matrix should be somehow that if you sum over J, Pij, it gives you probability of X equal to I. If you marginalize over I, it gives you Q probability of basically Q X equal to J. So I think we have an image here for it. Perfect, yeah. So think about you have these two distribution P and Q. This what you see in the center, transport plan. That's basically about the movement of actual data. And on the right, you see the distance is that penalty cost of basically movement. How much that is the distance between these 2 points. So if you look at this point I equal 5, this whole row basically tells you that if you try to move I 5 and move it to this Q, how do you distribute it basically? How much goes in this block, how much goes in this block, and so on? How do you distribute it? Then I equal 5, J equal 4, and this becomes the distance between them. So when they are closer, the distance becomes smaller, this dark region. They are farther away, the distance becomes larger. Now, the overall basically cost becomes P, whatever is the value from transport plan, times the absolute value of the distance, basically. That becomes the overall cost. And your goal is that to find this transport plan, this plan for this movement, somehow that minimizes that movement. Now, there is a marginalization here happens. If you pick this row, and marginalize it over J, so if you pick this row, marginalize it over J, you should get probability of X equal 5. Marginalize. If you pick this column and marginalize it over I, you should get probability of Q equal J. So that's how this matrix should be, this transport matrix. On rows, should some marginalized over one variable produce the probability of the other one? On rows and on columns, basically the opposite. So, okay. That's basically gives you the same thing. So overall, our basically distance basically becomes the distance between these 2 points. Optimal plan becomes we want to minimize this cost function, so that becomes our cost to minimize the distance between those two in that form. And that's for discrete only. If you do it for continuous, now it becomes integration instead of summation, and you still have some probability and the distance. So instead of P that we saw on the other one, you have pi, is basically the transport plan, and this becomes a norm over points minus each other, x1 minus x2, and again, it's not going to be discrete, so it's going to be integration instead of summation. Now, the full derivation for these formulas are also given in another slide. If you go on the repo, it says Wasserstein distance with the full derivation of these ones. But what you will basically see is that in Wasserstein's distance, we put these constraints on the gradients. So we enforce that whatever f we are using, whatever function we are using, if it's your discriminator, for example, whatever discriminator you have, the gradient of the discriminator should be less than equal to 1. Okay, and that comes from the Lipschitz constraints. If you remember, we had Lipschitz constraints before. The idea was that the function, we defined something called Lipschitzness and also beta smooth. Lipschitzness was saying that if you have a function, if you perturb it by perturb the data that goes to this function by amount, the output that you get, it should also change by like a kind of something like a similar manner. It shouldn't have abrupt, really sudden changes. That becomes a Lipschitzness. Then we have this beta smooth. Beta smooth says that if I have a function, if I change a data, perturb the data by amount, the gradient should also change relational with how much the data was changed. If you have those two properties, that means whatever model you have, it doesn't have a sudden behavior. If you change the data, it all of a sudden doesn't generate random. You enforce this basically behavior on the model. So here, when we say the gradient should be less than or equal to 1, that means it should be beta smooth. That means we're enforcing this model to always behave in a proper way. It shouldn't have any sudden changes in the gradients. However, in reality is that this is also an example of the continuous version. So we saw the image for the discrete, for the continuous. If you want to move this one to this one, this is the commutative distribution, and this is the distances between bins, basically. How much do you need to move that? Now, if we write this using the Adversarial times distance, this is technically becomes the final equation that we have, that we want to do some sort of like a maximization over this minus this. So for real data, again, the same thing, gap between discriminator result over real data minus discriminator result over fake data. P of xi is from real data. F here is the discriminator, the function, whatever you have. I is the real data that you receive, minus Q is the fake data. Fake data goes to the generator. So you want to always maximize this gap. Do a great job on finding real data versus fake data. The only difference here is that now we have this function enforced. That means whatever, this term tells you that you're looping, basically you're optimizing over all possible functions. And F, again, is your discriminator. Whatever discriminator you pick in order to maximize this should have basically beta smooth property. That means the gradient always should be less than or equal to 1. That's basically what this term tells you. Now, the challenge here is that, well, enforcing that property, the gradient of less than or equal 1, is not that straightforward for neural networks, right? So what we kind of like, it is some sort of like a workaround that we have. And the workaround is that we use something like a weight clipping or basically gradient penalty. So you clip basically the weights to ensure that it's always less than 1. Or you introduce some sort of like a high penalty on the weights or the gradients to ensure that it always should be less than 1. So that's how we can enforce that property. So you could pick a general like a GAN that you have and enforce this penalty over it. Right? It's kind of like enforce that, hey, I want to be sure that the gradient is always less than 1 to convert it to Adversarial time basically version in a dual file. Now, this becomes an image of for comparison. So if previously what we saw that the other version of the GANs, they suffer from vanishing gradient, because if the data of the real and fake are easily separable, the red line is your discriminator. It perfectly separates those from each other. So there is no gradient to go to the generator to improve itself, because it always gives you 0. It's like a perfect separation. If you use something like a Adversarial time distance, this becomes that loss function that we just saw. So even if you do a perfect scenario, you will still get some value for optimizing, because it has some information for the generator that how to change yourself, how to update yourself in compared to the other versions, because they don't have any gradients anymore, because it's like a perfect separation. Does that make sense? So again, in the red one, that's the general GAN, you perfectly separate these two. So there is no error, there is no backpropagation, correct? If there's no error, there's no backpropagation, there's no gradient that goes back, so there's no updates for generator. When you use Adversarial time, basically this cost function that you have is kind of look like this. So you will get error for like a backpropagate value, like a gradient for your generator. So your model will be able basically to learn as it goes forward.
So even if the discriminator is perfect, what's the need for?
Because your goal is not to separate, your goal is to generate.
Yeah, that's true. But what does that mean? What is the discriminator telling to the generator, like implication at least?
So here you have kind of like a,
What does it mean by loss function there? Like the value of loss function, what does it mean exactly? Even if the discriminator is performing very good, the discriminator is communicating back towards the generator that the thing you generated is not good. I mean, I want to put in words rather than mathematically. So what does it mean? The implication mean?
Yeah.
Sending some loss back, even though the discriminator is performing very good.
okay. So if your discriminator is performing really good, and discriminator doesn't care about the generator in reality, they are separate neural networks.
True.
Right? So the discriminator, his job is to separate fake from yes, and if it does a perfect job.
Yes.
The generator doesn't get any information about what did I do wrong.
Yeah, because it is not doing nothing wrong.
So that's not good for your training. Your goal is to have a generator, not discriminator. Correct? Your goal is to generate images. If you build a model somehow that your discriminator outperformed the generator, then you failed in the task of GAN. Your goal is to build a generator to generate images, not to build an image classification. You use the image classification idea to get rid of that likelihood concept, not to do maximum likelihood training, because I want to, instead of doing that, have another model that tell me you do good or bad. If the other model always beats you, then your generator doesn't learn anything. And those are all the challenges that GAN has. One of them is just the vanishing gradient. It gets to the point that the generator cannot learn anything, cannot update. So we update the cost functions, or basically the approaches that we take here, Western transistence. So you have, even if you're doing a perfect separation, you still give some information back to the generator that, hey, where did you do wrong? Right? So because again, the goal is not to get a good discriminator. Our goal here is to get a good generator. You can later use this discriminator for something else, but that's not the goal we have right now. Okay, so again, these are like just to basically a summary for GAN generator. Basically, just directed latent variables. It gets some Z, produce some data. The problem with GAN is that, well, it's not invertible, and there's no variational inference bit. That means that because it doesn't have an encoder. If you think about it, there's no encoder perspective, it's just generator. So you cannot get features perspective, information from GAN. You can only generate data and discriminate data. Now, that basically introduced new types of GAN. It's called BiGAN. Because the idea was that, okay, could we have GAN the way that it is? It does a good at generation, but also could we be able to maybe get features from it, like having an encoder concept? And that basically introduced this like a BiGAN scenario, and this becomes like the idea. So you still have the generator part. It's the same thing on top. Then you have this encoder here, so your data goes this direction, but also there is this one encoder that gets your data and creates some encoding, some embedding. Okay, so think about maybe I just draw this. So you have, I'm just going to draw the bottom part. So you have X, which is your data, goes to, and basically here we show like encoder, and then this gives us some H, some latent representation of X. Then you bring this, pass it this way, and you bring this also, pass it this way. Okay? Then you have Z, and Z here, maybe. And then Z goes to, here we see some G, and then we get GZ, okay? So latent goes to generator, give you an image, a new data. You bring this new data and the actual Z, put them together, like a tuple. And bring X and the hidden, put them together in a tuple. Then you pass a tuple to your discriminator instead of the discriminator before used to say get X and the new image, the fake image. Here it gets two types of data. Z and generated image, X and the latent. Okay, and the goal here basically will be to focus on basically learning not only the mapping and the discriminating between images, but also the latent features for the H. Because that way we can basically say that we are able to learn some features, some feature representation from the data. So you can basically ask back to from ByGAN, then, hey, what's the latent representation for this real image? You know, if you want to basically have those information, like a feature learning. So, in the after training, after you have this model done, you can generate a new sample by passing Z, a Gaussian noise, to the generator. Then you can also pass the X to the encoder and get basically that latent representation. Okay, so you now this way you have that encoder concept also similar to other models that we saw. So this becomes ByGAN, and I think that's it. All right, so just to summarize, what we saw today was the idea like there is types of generative model called GAN, generative adversarial. The idea for those models was that previous models that we have seen, they're working on KL divergence and the idea of like maximizing likelihood. And likelihood itself is not a good, basically method for certain development. Why? Because we saw an example that you can have a totally noise generated model, but you get a good result like over that. Like you get a high likelihood, not good result. You get a high likelihood over the really, everything is noise. So the idea was that how could we train these types of model or some generative model becomes like a likelihood free. And that becomes the idea of GAN. And the idea was that, well, we could do some sort of like a two statistics test, like it's kind of like a t-test to compare the probability, the distribution over real data versus distribution over fake data, and try to see how similar they are. And then we say that, well, that's like a t-test and stuff like that, they're not that easy. So let's, instead of we trying to define that, let's use a neural network discriminator. That's job is to separate this, give us the same statistics, good or bad. Then, what we also saw that, well, for that discriminator, there are different ways that we can measure the basically separation. We saw that KL divergence, but then we saw that the Shannon basically divergence. Then we say that, okay, all of this, they have some issues. And one of the important one is the vanishing gradient, with like, for example, mode collapse. And then we say, okay, let's introduce new types of divergence. And one new divergence was F divergence. The idea of F divergence is that it's similar to the concept of KL divergence, but you define the function that you want to use for divergence. And that function basically has some properties. It should be convex, it should be lower semi-continued, and it should, at F1, it should produce 0. Okay, so that should be any function like that that you can find, you can use it as part of F divergence. So the benefit of this F divergence for GAN is that now you have a freedom of deciding what cost function that you want to use, as long as it basically satisfies the constraints. Then we also say that, okay, there's still some challenges with even with F divergence. And then we introduced Wasserstein distance. And the idea of Wasserstein distance or WGAN was that if I want to compare two distribution, one way of this comparing this statistic is that to see how much effort basically or I need to put in moving one to the other one. And I want to minimize that effort overall for moving one distribution to the other one. So our goal will focus on minimizing that effort basically. And then we also talked about like a concept like the ByGAN, that which the idea was that, well, even in the Wasserstein distance or general form of like all form of like GANs, you don't learn any latent features. If we want to learn latent features, GAN doesn't have encoder, that's why. So what we do, we just introduce an encoder in the training. So not only we generate image, we also learn latent representation over the data. So we can answer questions later using that. So that is like the summary of what we saw. All right, let me see.